I'm Natalia, I'm a lecturer at Bournemouth University, and today we'll talk about Erlang and how we can scale robots. So first of all, who I am, as I said, I'm a lecturer, and the research I will talk today is in collaboration with these beautiful and wonderful people. So my colleague and supervisor and teacher, Phil Trinder, many of you probably know him. He works with distributed systems, the scalability, parallelism, this kind of things. Very good friend for many years now, Gerardo Aragon Camarasa. He works, so they're both at Glasgow University. He works with robotics vision, and a couple of our students, so Adam, he now works at Amazon. Andre does her MSc in Sweden in robotics. So there's a beautiful people that help to do the research, that we're actually doing the research. Well, the next thing is the robots, right? What sort of robots are we going to talk about? We'll talk about cooperative robotics. And the thing about cooperative robotics and the challenges that it poses is that it is a distributed system, but it's not our classical distributed system. It's not anymore in the room, it's not closed, it's not safe, it's not, we can't protect it, we just can't put a firewall on it, right? So these are just devices. They have a lower power, they have quite limited computation resources, limited power resources, and then a single robot, it's not just one single machine anymore. It's a collection of machines. So we see a robot and we think it's a drone, right? So it's like a PC, we can think of it as a PC. No, we can't, because it moves around, it can be multiple, boards actually they're connected and communicating to make, these robots moving. And then it's lots of challenges. We can't protect it the same way anymore. And then they crash, right? So drones flies, suddenly it drops, and that's it. We need to do something about that. Another thing about cooperative robotics, it's not swarm robotics. So there are some common things here that are common to swarm robotics, the number, for example, and that they work all together. But the functionality is very different. So swarm robotics, it's very much about emergent behavior, in that each of the robots, it's this tiny, simple thing that just, does very simple movements, like forward one step, backwards one step, things like that. And behavior emerges when all of them are together in vast number. With these robots, each of the robots is complex. Each of the robots is individual, and each of them can do lots of, complex and wonderful things. But when they come together, they can do even more. So they work on some common task, and each of them has a behavior already. And then when they come together, emergent behavior also comes, but it's not their only behavior. They have their own behavior as well. Right? Another thing is that they cooperate. And cooperative robotics is different from collaborative robotics, right? So collaborative robotics is very much about working with human in the same space, right? So identifying that the human is nearby, identifying visual expressions and things like that. Cooperative robotics is very much about the task. So here, the focus is not on the human, the focus is on cooperation, in doing some kind of a task together. And it doesn't matter whether that's a human, that's a robot identical to this particular robot, or a different type of robot, just doing, some common thing with other robots. And they all contribute to the common goal. So we set the scene, we know what types of robots we're talking about now. Middleware. And there are lots and lots of middlewares for robotics, right? And these are just the open source, so just, and those that have logos, right? So, because I thought, well, I can do a list, but then it's a lot of work, right? So that I'll just take logos. And these are these ones, and they're sort of more or less supported. They have a community, they have these kind of things. So quite a lot of those. But then out of all this, there is ROS. And ROS is the most popular. And actually, it took out of the market many of those. And some of them, some of maybe not these ones, but others that I didn't mention, they stopped, the researchers and developers, the community stopped the support just because ROS appeared. And in comparison, ROS is just huge, and those have just, you know, tiny, small communities. So a little bit about ROS. So what is ROS? ROS is Robot Operating System. It's not actually an operating system, it's middleware. It works on top of usually a Linux operating system. It is working since 2007, and the reason for it to be is that no single institution, even institution, can cope with the variety of robots and all the aspects that must be covered, right? So they decided, okay, we need something, and they came up with ROS, and it is tools, library, and conventions. It has quite a large community. This picture is actually for quite a while, but they don't update it. I think they just don't look into statistics or something like that. But this picture is from a couple of years ago, and as you can see, it's quite popular in Europe. It's quite popular in North America, Japan, a little bit of Australia. But the thing is that every community that works with ROS actually works with robots actually works with ROS, you know, in one or another capacity. It's not particularly popular in industry, but what they do is that they take ROS and they try ideas there, and then they bring those ideas in those proprietary software. The reason for that is that ROS has quite a number of really interesting philosophies. So one of them is using as much or as little ROS as you like, right? And this helps a lot. So you can put, you know, all sorts of functionality, movement cameras and things like that, and then you need to do face recognition, for example, and you work on that specific library. You do research, you do lots of experiments, and you get from ROS all this state-of-the-art movement things and, you know, other drivers. So you don't need to worry about that. So a little bit overview, so what ROS is. So it has a modular structure. It has nodes, and each node is responsible for some kind of functionality, and then we connect those nodes. They have publish-subscriber sort of message communication, right? So some node, for example, wants to publish something, some kind of information, and just publishes. And other nodes that want this information, just they subscribe. And they can subscribe to any rate they like, so it's quite flexible. And then we can have this on different robots, so it can be distributed. And then we have a ROS master node. And the interesting thing about this ROS master node is that to be able for ROS nodes to communicate with each other, they need to be registered with ROS master. But the communication is not via ROS master. ROS nodes just communicate with each other. But if nodes are not registered, they won't be able to communicate. But then, you know, we started working with robots and ROS, and people are saying ROS is not scalable, ROS is not reliable. And then it's just like a folklore. People say that it's not. So we decided to check what's going on there. And first of all, of course, we looked at ROS. And then even before you start doing any experiments, you see quite a lot of things here. So first of all, that's ROS master. It's because it's a single ROS master for all group of nodes, it means it's centralized registration, which means it won't scale beyond 10 devices at most, right? Another thing is that fault tolerance, there is no actually fault tolerance. So the way they introduce fault tolerance, there is this file called ROS launch, and it's actually was created to launch ROS nodes. But then they figure out, well, it launches them quite nicely, and then it can recover them. Why not to use that for fault tolerance? So they use it for that. But the two quite interesting things that ROS was never designed for scalability. It was never designed for fault tolerance, right? It was designed for roboticists who work with specific things, and for them it works perfectly, right? It uses Python and C. So the question comes, how scalable ROS? So Gerard and I, we had a group of students, and the first thing that we decided to do is to analyze ROS scalability on a single robot, right? So we single host, right? Simple robot, single host, and we took just a laptop, and then we wanted to see how scalability is and what the parameters that impact scalability. So what we analyzed was latency and throughput, 2 parameters. And then the experiment is really simple. We have a publisher, we have a subscriber, and we have a reporting node. Just 3 nodes. And then they exchange messages. So this node publishes, they subscribes to it, and so on. And then here we just do the recording of what's going on there. Very simple. So the things we thought to look at was message size. So whether message size can impact on scalability within a single robot. Then languages, C or Python, which one is better? Is it C is like, so the obvious question, of course, it's C, but whether it is, the question is. And the second thing is how frequently we send the messages. And then this is just a bit of configuration for those who are interested, what we did. So we had a laptop, and we have this Python, ROS, and we had ROS Pi, a couple of libraries for ROS, and it's Ubuntu. So we ran the experiments, and a couple of things that we realized was that message size within a single host doesn't matter. What matters is the queue size, right? So when we publish things, there is a queue, so the sender has a queue and the receiver has a queue, and that queue has an impact. So if the queue is sufficient, then we have a good performance, latency, throughput, everything is fine. If the queue size is not appropriate for a particular rate and particular size of messages, then that's it, we have an issue. C and Python, and actually the frequency with which messages are sent within a single machine, they don't have any impact, so they don't matter. And these are some interesting findings that we found. So we're looking at message queue size, at what's going on here, right? So here we have messages, so they're just messages we send, and here we have the latency. Right? These are in nanoseconds, but it's sort of microseconds. Sorry, you can't see it properly. But anyway, what's going on here is that we have quite small messages, only 2 bytes. And then we start sending them with 1 megahertz, kilohertz, right? Is it kilo? Yes, great. Oh dear. I forgot the kilo and mega, my God. Right, so kilohertz. And we have this one, then what we do, we increase the size of the messages. And we get, so this bit is the same as this one, but after that there is this spike, and then messages, go this funny, frequencies. Sometimes it's high, sometimes it's low. Then we decide, well, let's check what's going on. Let's increase it. And then we don't have this spike anymore. The messages just, went up, and some of them have a smaller and everything. And then what we did, we decrease the frequency, right? So the frequency now is much slower. It's not 1,000, it's just 10 hertz. And we see what's going on. And actually, the frequency got back to the sort of, the latency got back to the stabilized state. So it just shows that the queue size has a huge impact. What's going on is that when you publish, the publisher, if it published to the queue too quickly, then it starts dropping messages. The same happens with the subscriber. If it can't absorb messages quickly enough, it starts dropping them. So that's what we observe here. Another quite interesting observation I thought to show you was C and Python. Interesting thing that so the experiments are on bytes. I don't remember the frequency, but it doesn't matter. So the thing is that if you work on a small message size, right? So for example, you work with sensor data, not the videos and things like that, not the voice, but sensor like distance, temperature, this kind of messages. Then up to 4 megabyte messages for kilobyte, oh dear, for 4 kilobyte messages. it doesn't matter which library you use, which language you use. You can use Python and see the performance is just the same. It's when your messages size goes up, you work with videos and things like that, then when you need to switch to C. So on the low size messages, it doesn't matter, they perform identically, whereas for the larger sizes, sort of Python stops, progressing, whereas C, the throughput grows, so the performance is quite good until, messages become quite large. Right. So that's within a single machine. Then we thought next step is to analyze the scalability, the performance when we have multiple machines. So we've got these car-kit robots. The reason for that is that they're quite cheap. So a single robot like this will cost you around 120, 150 with everything, with Raspberry Pis, with all sorts of cables, all the router, everything. So it will come around 150 pounds. And they do experiments that we need. We have robots, and they can talk to each other, and we can run the experiments. So we did a couple of experiments here, and the first one was scope experiment. Then we used representative data. I'll explain what that is. And then we used vertical experiments. I'll also explain what that is. So here we have robots. In this particular picture, we have 3 robots, and then we also had Raspberry Pis. But the main experiments that we ran, we used them like this. So we had Raspberry Pis connected with the router, wired. And then we have robots, router, Wi-Fi connection, and then the master node, it was separately. So we didn't put master node on any of the robots, we just put it separately. Right, interesting thing, for those of you who want to start or thinking of starting working with robots. The lesson, I suppose, the main lessons that we learned is that starting simple as possible. That at the point when we could understand everything about those robots. So the reason for that is that for this specific experiment, we started really cool. We said, oh yes, we will measure that. What we will do, we'll take this demo and we'll do the robots move. Maybe you saw the video. There is a girl and she's walking, and then there are 3 or 4 robots and they follow her. And we thought, well, that's cool. That's really nice. We'll do the same. Well, we sort of started doing that, and then we saw some funny behavior, and we couldn't understand that. Then we thought, okay, we will simplify. Robots won't move, they will be stationary, and we'll see what's going on. Again, and we were stepping back, until we got 2 Raspberry Pis, wired connection, and they were exchanging just 1 ROS node per Raspberry Pi, and they were exchanging single messages, right? In one direction, and then in another direction. That's how simple. And only when we get to that stage, we started understanding what's going on there. Right, so vertical scalability. Vertical scalability is that when we explore the number of nodes that we can use, right? Usually vertical scalability within a single machine. But we're interested in distributed systems. So we thought we will do some kind of a mixture, hybrid. So we have 2 robots, and then we increase the number of ROS nodes in each. So sort of vertical scalability, but in distributed sense. And this is what we have. We have 2 robots. We have a number of ROS nodes on each robot. And then those pairs, they exchange messages. So nothing complicated here, just exchanging messages. So experiments that we ran were Raspberry Pis. So there were just 2 Raspberry Pis, and we ran the experiments. We are Wi-Fi connection, and then we used car-kit robots just to confirm that our experiments are consistent and we understand every step of that. And then we used representative data. So what representative data is? In our experiments, these were very simple messages. They were just exchanging, I don't know, string, some size, and we're just exchanging it. And I said, well, how valid our experiments will be? Can we actually generalize on that? Can we draw a conclusion? Are our conclusions valid? So we did there is this PR2 robot. And in 2011 and from January until September 2012, they were collecting data from this robot. And there were a couple of real sensor data and there were video data. And there is quite a large collection of that data. And the data often used by roboticists to, check some kind of a concept because these are data from real robots. So we have two data, sensor data and video data. And the main actually difference is in the size of the messages. So the frequency is different. It's 20 on the sensor, 30 on the video one. But the message size, that's where we have the difference. For 25 kilobyte and 300 kilobyte, so 100 times larger. And this is what we found. So we plotted, here we have the message latency in milliseconds. We could adjust that, but oh well, maybe next time. And then message IDs. So we were sending 1,200 messages, and for each message we would record the time it would take. So what it did, it would send a message and return back, and we see the latency, what's going on there. So when we have 2 nodes and 4 nodes, so it 1 per robot, right, and 2 per robot, the latency is consistent, so everything is fine. As soon as we start increasing the number of robots, the latency goes up, so it means that we have delays there. And then at some point they will just start breaking. They don't, there is a collapse, we can't do it any further. And that's it.
Excuse me, can you point to the colors, because I can't map it because the light is...
oh, right, right.
On the right side.
Right, so 2 and 4, they're on the bottom. So the latency is almost 0, like it's here. Then when we have 4 nodes, so 4 nodes per robot, 4 and 4, the latency starts increasing slightly, but quite slightly. Then when we have 16 robots, so it's 16 nodes, it's 8 nodes and 8 nodes, they start falling. And then from that point, they just, go worse and worse. And we run experiment up to 256 nodes. So it's 128 per robot, right? So they start. So the spike here, so you may get surprised why it goes down, is that because some of the ROS nodes start falling, right? So they don't use the bandwidth anymore, they don't communicate, so the remaining nodes start using that. Is that clear? Yes. Great. So interesting, and the most important observation that we found is that there is so-called communication scaling limit volume. So in our little group, we're very bad with names, so this is the best we could come up with. And we called it SCLV. So if somebody, comes up with a better name, please tell us. This is the most our imagination went for. But the thing is, the result of it is that there is this volume, and it's stable, right? And it depends on the number of nodes, frequency of the number of nodes, frequency, and message size. This is the message size. And if we start changing any of the parameters, it gets impact on other. So what it means is that if for a particular group of nodes, we can find this volume, then by changing, for example, the frequency and the message size, we can identify what the maximum number of nodes that we can support there, right? And get the beautiful performance. So that was the jewel of this research. Another experiment that we did, again with Phil, Gerardo, and Andrea this time, is to look at fault tolerance. Right, so those 2 experiments, they were about scalability within a single robot, between robots. Now we want to look at this at fault tolerance. So what's going on with Erlang's fault tolerance, how bad or good it is. So what we did, again, we took a laptop, we took a camera, and it can, tilt and turn, and we did face tracking, and we implemented in ROS. So we have ROS node that collects all the information, ROS master, and we have working nodes that do the face recognition. You know, the more that we have, the sort of so they work on different algorithms. So what you do, you try to run them across as many algorithms as possible, and then you sort of get the results, merge them, and you get a picture. So, and what we found, so this is what we've got. This is the quality index, and this is the number of the frames. So we had up to around 100 frames. And the green one is the one that was running without, so we pre-recorded the face, and we knew the number of frames, and now we want to start killing the nodes, right? So the green one is when everything was fine, and you don't look at up and down, it's fine. What you look at is that they need to concur, they need to remain the same. And then the blue one is when we did a gentle kill. So we set a kill request and they were sort of gently terminated. And the red one is that we just terminated, didn't ask anybody. And this is what we've got. So what it says is that after we started killing 10% of ROS nodes, the system never got back to the initial state. It just deteriorated. And eventually when we did the kill, it just failed, right? Completely, that's it. No recovery anymore. So how you can see that? Well, when you do the face recognition and you have this rectangle, right? It starts, getting slow, right? And doesn't, quite catch up. And in the end, it just failed. So fault tolerance is not particularly good. So what we need to scale ROS, right? That's the answer. We need to scale, we need to introduce fault tolerance, and because we had this conference, that's of course Erlang, right? We do that with Erlang. What else can we use? But idea of Erlang in robotics is not particularly new. There were other people before us who did the same, and unfortunately, right, I will talk about that later. Curl, so there is this curl, and it was at Kent University, it's in the UK. It's quite well known, it's about Erlang in robotics, but it's not exactly Erlang in robotics. It's about teaching Erlang in a fun environment, right? So there is this simulator and you can actually run the robots. So that's instead of, having these lectures when you describe and, try to explain students and inspire them somehow that Erlang, it's cool and you don't, care about this, learning curve, doesn't matter, there is fun in the end. So they decided to do this fun with robots. So the students sort of get excited about robots and start using Erlang through that. So that's curl. There was Razan, and Razan is from the University of Catania. And specific aim that they had this team of robots that played football. Probably you heard about Eurobot. And those robots, they play football, and they wanted completely new operating system for those specific robots. So they had, so they wanted a complete framework written in Erlang, and it goes like from really bottom to the up. So from low-level control levels to high-level imperative levels, and on top of, so initially it wasn't called Razan, it's when they introduced simulation engine in there, then they called it Razan and it got its name. I'm not sure if it exists anymore, or in this particular form there is any research in there. Last time I spoke to the person behind this, they stopped it, and there are a couple of reasons for that. The first one is that it's quite difficult to find developers and stable interest in Erlang to keep developing it. That's the first reason. So they rewrote, I think it's in C. At the time they were saying that they're rewriting it in C because there is just much more opportunities, because this was at the university, so that would be students and research students and postdocs who would do the work. So with C it was much simpler. And then the second one was popularity, right? It's not as you know, the success behind ROS was, it's not just one university working on that. It's the whole world works on different parts of ROS. And for a single institution to maintain this thing, that's really difficult. There is another project, and it's called OPENRTMAIST project. And AIST comes from the name of the university in Japan. And it's also open source. It's based in Kobe. And you know, it provides communication services, central control programs. And when they started with this, with this OPENRTMAIST project, the aim was just to introduce this monitoring tool in Erlang. But then they saw the beauty of it, and they implemented actually it in Erlang, and it supports, but for some reason it says unofficial. I suppose the people who are behind that, they decided not to include it. But it says that it supports Erlang, but unofficially. So these are just some examples. And when we looked at it, there are a couple of reasons that prevented other projects to actually be really successful in that area. And one of them is, and it's not only about Erlang, it's all about all other, you know, projects that were in different languages. It's all about middleware in robotics. And the first thing is, it must be adopted by the community. That's the foremost thing for it to go forward. And the reason for that is that it must be easy to use, and it should enable roboticists work on it, right? So the people who actually work with ROS, these are not computer scientists, these are engineers, and these are people who are interested in, for example, in vision, in movements, in, you know, all sorts of things, but their least concern is programming. So what they want, in majority, is that some, you know, simple, really simple interface with a little bit of Python that they can run. And of course, they don't want to learn another language. In particular, they don't want to learn Erlang. So the reason for that, like it's a first-hand experience, I would say, because Girardi, he worked in a chemistry department, and there they were working with this robot for chemistry that would, you know, mixed all sorts of things, you know, together to come up with new elements that in Glasgow University. And he worked for a year there, and he wrote this beautiful thing in Erlang, and it was fast and it was cool and everything. But he was the only computer scientist in the group, right? And the rest were chemists. And they were so much not interested in Erlang and learning the language. So in the end, even though the Python version was like slow and it didn't do what it meant to do and things like that, they still stick to it. Because it's Python, it's simple, and they don't need to worry about anything, right? So when working with these things, we need to think about people actually who are going to use this operating system. Large community of contributors is very important because it means state-of-the-art libraries, state-of-the-art, you know, things that they can just take, somebody already developed, and they focus on their particular thing. The philosophy of ROS, you know, as little as needed or as much as needed is also important. Ability to work with other middleware is really important. And then modular approach, you know, when we can have different parts. ROS, although didn't have a success in industry, so it's vastly popular, it's like the thing in academia, but it's not used in industry, and there are a couple of things for that. Performance, fault tolerance, security, and I suppose developers is another thing, but it's the same thing with industry. These are just the people who are going to work with the thing. So fault tolerance and security, these are obvious. Performance need to be. So what industry usually does, they check the thing in ROS because it's simple, right? They can check the idea, and then they re-implement it in their proprietary hardware. That's what they do usually. So our idea, what we want to do, don't want to re-implement the wheel. We want just to replace the communication layer, right, with the interfaces. That's our goal. We want to keep ROS as it is, so nodes, functionality, libraries, everything. We just want to change the communication layer with Erlang. And here we need to keep in mind that there are two things here. So the first thing is within a robot, right? Because we have different nodes communicating, ROS nodes communicating with each other, and then we have different robots that also need to communicate with each other. So these are our idea. So just to try the idea, what we did, we implemented, so the same face tracking, and we implemented, as I said, in ROS, and the second thing we implemented in Erlang, right? So Erlang here does only communication. Yeah, I'm finishing. Only communication. The libraries we didn't write, so all libraries are ROS libraries. So just communication and recovery, those processes. And that's what we saw. So we have ROS, we saw this picture before. We killed the process, they go astray, and then when we kill it sort of brutally, it never comes up and it's only 10%. Then we came with Erlang, we did the same, we killed, but this time we killed 50% of the processes, right, half of them. And what we observed is that in both cases, the system recovered and they just continued working. And when we killed 25% of the process, system even didn't notice the 20% of processes gone, right? And the reason for that is Erlang has very light processes, right? So they die, we can recover them very quickly, so the recovery time is very quick. Supervision, because Erlang supervises the processes, so that's the reason, you know, that's something, I'm sorry, and recovery mechanisms. There, yeah, I need some water. Sorry, break. Right, so recovery mechanisms, they're inbuilt, right? We can recover all, recover parts of them and so on, kill everybody, kill myself and things like that. So that's the beautiful things about Erlang. The process is so light and there is supervision mechanism. So the potential here is really, really huge. So what it means is that Erlang, it doesn't only reduces the failure, it also mitigates the impact of failure. So we don't even notice that something went wrong. Well, you know, with the success of WhatsApp, I think it's not particularly surprising, but it's nice to see that it also works in robotics. Right, so what's next? So next is we've bought some robots, some boards from Peer, and Germany made, and we hope to run some experiments with that and try to see what's going on there, maybe replace our Raspberry Pis with that. But for that, because I work in academia, I need students, I need money, so we're writing at the moment a couple of proposals, hopefully we'll be successful and not reliant on our students that much. Because the funny thing is that, you know, when we get really nice students, we just leap forward and we get really nice progress. We find really interesting insights, but then we just sit quietly until those beautiful and wonderful students come and do research with us. Another thing is autonomous mobility that we're interested in, just looking about distribution between robots. So that's something I'm also working. Thank you. If you have any questions, please ask. Thank you.
I think that was awesome. I hope you all agree. So we have a couple of minutes for questions. Anyone wants to ask anything? No questions?
It was awesome. Yes, please.
If I understood correctly, the master node, so every child node has to be registered
Yes.
mastering node, but you mentioned that master node actually doesn't have any place in the
Yes.
collaboration itself.
Yeah, yeah.
So what will be if once a two-child node is registered in
Yeah.
the master node
Yeah,
and master node dies?
yes.
What will be the impact?
That's it. That's it.
Nothing.
Nothing, yeah. So what they actually do now, so that's the one thing that, thank you for the question, it's a really good one. So we now want to remove master node like at all, we won't have it in this, new communication, because currently what happens, first of all, it's very difficult to understand what's going there at all, right? Because there is this huge robot, and it does something, and then it stops, right? And it's not particularly clear what's going on, whether it froze, whether something died inside, whether it's just, thinking slowly. So what they do, so a robot, for example, like unfolding clothes or something, it's a huge one, and it moves really, slowly, and you won't believe that it's actually unfolding, and sorting clothes, but it does. And, suddenly it starts moving, so they wait 10 minutes, they wait 15 minutes, nothing happens, and 10, 15 minutes, it's fine. It's like, maybe it will, it's thinking. So when nothing happens, they start restarting it. So they switch it off, brutally like we do the reset, and then it restarts. But it's simpler to wait, 15, 20 minutes. Maybe it will, wake up and continue working rather than restarting it, because it will take even longer. So at the moment, if something happens with ROS-node, and that's another reason that we put it separately in our experiment, if something happened to that, that's it, the system crashed. The only thing is a human comes to that robot, pushes the button, and restart the system.
Any other short questions? Okay, thank you so much, Natalia.
Right, personal one.